The most commonly used method for duct sizing is equal friction method. What is equal friction method? It assumes the pressure loss throughout the duct per meter is consistent throughout. So every 1 meter, let's say there's a drop of, we assume that there's a drop of maybe 1 Pascal or 1.2 Pascal, and the pressure loss per meter is consistent all the way from the start where they just come out from the AHU until the end when it reach the diffuser. So usually a friction loss value of 0.8 to 1.2 Pascal per meter is used, but in special circumstances there may be a variation of this value. So in order to use the equal friction method, you have to know how to use this chart called the friction chart. So in a friction chart, there are actually 4 properties, as you can see from the 4 categories of lines, mainly the horizontal lines, the vertical lines, and the 2 slanted lines diagonally to the left and diagonally to the right. So the 4 properties include friction loss, which is the term that we have just discussed, is in Pascal per meter. And the horizontal axis over here is the air quantity. Air quantity is the volume of air that the particular air duct section is carrying. So the units that is used is in liter per second, and the other commonly used unit is actually cmh. That means cubic meter per hour, and you can do the conversion easily. Next, with that, the diagonal line, one of them is the duct diameter. So with a certain friction loss and with a certain airflow quantity, that you will be able to get a equivalent round duct diameter that is able to transport this amount of air that you require. And the other slanted line is the air velocity. So note that air velocity and air quantity, they are actually different. Air velocity is in meter per second, which is how fast the air is moving. Whereas for air quantity, it is in liter per second, which means how much air the duct is actually transporting. So let me write down the four terms again. So first up, you have air quantity. Air quantity is in liter per second. Secondly, you have the friction loss factor. So friction loss factor, the units is in Pascal per meter. So with these two, let's say we assume a certain value of friction loss from the start, and the air quantity you should be able to have once you know how much cold air you need to supply to the room in order to remove all the heat from there. So this is usually retrieved from after you have do your heat load calculation. So once you have these two, you will be able to get the other 2 quantity. The first is round duct diameter, and which is in terms of millimeter, and the last one is air velocity. And with this round duct diameter, as we have mentioned before, is not really commonly used in a building space, especially with ceiling constraint. So from round duct, you should be able to get an equivalent rectangular duct by using some form of conversion. So, and air velocity will change throughout the network, the air transport network, because as the duct size change from the biggest when it just come out from the AHU until it gets smaller and smaller and smaller when it branch out, the air velocity will change accordingly. So if we take a lower friction loss value for our design, for example 0.8 Pascal per meter, compared to a higher friction loss value, let's say 1.2 Pascal per meter, what will be the difference? If you chose a smaller friction loss value, the duct size will be bigger. When you use a friction loss chart, you'll realize that the equivalent round duct diameter will be higher. However, the air velocity will drop because the bigger is the duct, the smaller will be the air velocity due to conservation of mass. And because of the lower air velocity, the static pressure loss will be lower. So it makes sense to actually choose a lower friction loss value. But why don't we do that is because the duct size will have to be much bigger. You have to upsize your duct, and you will have a higher capital cost compared to choosing a bigger friction loss value where you will get a smaller duct, but that of course will cause a higher air velocity, which in terms will cause higher static pressure loss, which means the AHU fan will have to work a little bit harder in order to transport the air through the smaller ducting network. Okay, let me use a simple example to demonstrate how to use the friction loss chart to size a duct section. So first you have to know what is the airflow quantity that is passing through the particular duct section. So as you can see over here, there are 4 diffusers, and each diffuser is transporting 100 liters per second of air. So CD, CE, FG, and FH will transport 100 liters per second of air each. So over here, it will be 100 liters per second and 100 liters per second. How about BC and BF? How much air must pass through this section before it can split up into 100 each? So BC and BF will each carry 200 liters per second. So 200 liters per second of air must flow through these 2 sections. And finally AB, which is the main duct when it just come out from the AHU. So this duct will transport all the air required for all the diffusers. So obviously it is transporting 400 liters per second of air. So there are 3 main volume here, 3 main airflow volume, which is 100 liters per second, 200 liters per second, and 400 liters per second. With these 4 air volumes, let's plot onto the friction loss chart and to retrieve the round duct diameter. But before we can plot onto the chart, we need to assume a friction loss value. So if a friction loss value of 1 Pascal per meter, and with the different airflow quantity, we will be able to plot the 3 points. So first, we have 100 liters per second for all the small duct section at the end. So 100 liters per second is over here. And 1 Pascal per meter is over here. So the intersection point will be at this part. And after you plot this, you can read off what is the round duct diameter that you should size. So this particular line is 160 and this particular line is 200. So this point over here, it will be around 185. So all the small section, you should have a 185 millimeter round duct. How about 200 liters per second, which is the middle section? So 200 liters per second is over here. So after you plotted the point, you can read off the round duct diameter again. So this is quite close to 250 mm. So 240 mm will be a good estimate. And finally, AB, which is the biggest main duct that just come out from the AHU, it should be, of course, the size will be the biggest as well. So this is 200 liters per second. The next line is 300 followed by 400. So you will look upwards vertically until it cuts 1 Pascal per meter. So it is over here. So this is your section AB. So section AB cuts around 350 mm. So with that, you have sized up the 3 section and you have retrieved the 3 round duct diameter. So let's also read off what are the 3 respective air velocity. So for the first section, the smallest duct, it is between 3.5 and 4. So the air velocity is roughly around 3.7 meter per second. For 200 liter per second, the middle section, it is between 4 and 5. So over here is roughly around 4.4 meter per second. And lastly, the biggest air duct, which is duct AB, is above 5 meter per second, is slightly away from 5 meter per second, so maybe around 5.2 meter per second. So as you can see from here, once you have assumed a friction loss value and you have the different airflow quantity at the different duct section, you will be able to get the other two values, which is the round duct diameter and the air velocity. Okay, now if we want to convert the round duct into a rectangular duct, you have to use such a table to find out. So the numbers that you see inside over here, the numbers that you see all over here, they are the round duct diameter. And the number that you see at the left hand side and at the top, they are the two sides of a rectangular duct. So one side of course is A, the other side is B. So for example, if I have a round duct of 177 millimeters, you can get an equivalent rectangular duct of 175 multiplied by 150. So 175 multiplied by 150 is equivalent to having a round duct of 177. Okay, so the problem is not all the numbers, as you can see, the numbers here are unique. So for example, our first round duct diameter that we are interested in is around 185. Is 185. So let's go and look for 185 over here. But you may notice that there are no 185. Alright, you have 183, 181, 189. So these are the few round duct diameter that is quite near, and you can actually use this value as long as it's not too far off, maybe plus minus 5 to 10 mm. You can actually choose that particular value. Okay, now there are three choices. So does that mean that we should choose the one that is closest to 185? In this case, is 183. And if you choose 183, what will happen? The rectangular duct will be 300 multiplied by 100, which gives you an aspect ratio of 3. And as we have learned in the previous topic, we should choose an aspect ratio that is as small as possible for all the various advantages such as lower capital cost, lower operating cost. So you should always choose an air duct that is close to the top over here. The best is the first value over here, because this will give you a square duct. For example, 225 times 225, 250 times 250, they are all at the top. So if it's just one or two rows below, it is still quite okay. The aspect ratio will be quite okay, but you shouldn't choose any duct that is far below. So this part over here, although there are a lot of duct sizes over there, but it's not practical to choose, for example, a duct of 1008 multiplied by 150. You will get a super long rectangular duct, which you shouldn't see in a building operation. So back to our question, for 185, we should choose this 189 duct. So we will take 200 multiplied by 150 to replace the 185 round duct. This part we have done, so we should choose 200 multiplied by 150 mm, which is this particular duct section. Okay, so FG, FH, CD and CE is similar. So this is similar to 200 times 150. Let's look at 240 mm. So 240 mm over here, there is a 244 or 246. So either one of these will do. So maybe let's choose the better one, which is the square duct. It will be 225 times 225. And finally, AB is 315 mm. So 315 over here, there's an obvious choice. So 314 is very near to the round duct diameter, and also is very near to the top. So 314, and we will take a rectangular duct of 300 multiplied by 275. 300 multiplied by 275 mm. So as you can see, other than having space constraints such as ceiling height is limited, as far as possible we should always choose a small aspect ratio duct. That means try to choose those that are near to the top and never choose those that are below. And maybe let's do one last extra step, that is to calculate the various aspect ratio. So aspect ratio for 200 times 150, it is around 1.3. As for the second one, 225 times 225, aspect ratio is 1, which is the best that it can get. And finally, 300 times 275, the aspect ratio is 1.1. And as you can see from here, all the aspect ratio are quite good and within a good range.